This is an example of a little bit more difficult word problem. So you have two observers, and you are given that they're standing 1,500 meters apart, and you have a helicopter floating in the air, and one observer is viewing it from 32.5 degrees, and the other observer is from 1,500 degrees. So let's draw a picture. And so the bottom horizontal one is the 1,500 meters apart they are, and this guy on the left is, here's going to be the 32.5 degree angle, and then this guy is standing over here and he's at 51 degrees. So let's drop a perpendicular down and label the uppercase H as helicopter, and then H is the height of the helicopter, and X, because we've drawn the picture pretty descriptively, is going to be the distance to the nearest observer. So let's fill in the rest of the measurements that we have. And the first thing that I did was I started out with writing a trig expression that was pretty easy. We know that we're going to work with the right-hand triangle, and we know that if we took the cosine of 51 degrees, the one that we were interested in, we have d over x. Well, but then we notice that we have three variables, h, x, and d, and we're trying to figure out how to make some progress. So we think, well, we notice that the left triangle over here this left triangle has trig ratios that we can write in terms of h and d, and so does the right triangle have trig ratios that we can write in h and d. So we think we can write two equations, two unknowns, and let's go ahead and do that and see what comes of that. So we can say that the tangent of 32.5 degrees, the triangle on the left, is equal to opposite h over adjacent, 1,500 minus d. Well, we can write a similar expression for the triangle on the right. Tangent 51 degrees is equal to its opposite, which is also h, over its adjacent, which is d. And so we can solve these two equations for h. We could have solved them for d as well, but h, if we solve them for h, then we can say h equals tangent 32.5 degrees times all of the denominator, 1,500 minus d, and we can say that h in the bottom equation, multiplying both sides by d, is d tangent 31. Well, if they're both equal to h, then they're equal to each other, so let's write that equation. Kind of ran off the page there. Okay, so let's write that equation, distributing the tangent 32.5 degrees. And so, but we're trying to solve for d, so let's shove it all to one side. The 1,500 tangent 32.5 degrees is all on its own on the left, but then we're going to factor the d out as we add this expression to the right. And so we get an expression solved for d, which is a little bit complicated, but we haven't used the calculator to come up with an approximation. We'll just keep it exact. And so we can crank that out and find that d is approximately 510 meters. But what we're going to do is we're going to use the exact value, this, in our calculations from now on, instead of the approximated 510 meters. So we found d. We don't even want d though. We want h and we want x. But we can go back to this equation here and plug in the value of d that we found. Of course, like I said, we're going to use the exact value and plug that in the top. And there's the denominator. And if we crank that out, x is approximately 810 meters. Okay, so we have 1, the answer to 1, but we need to find h. And I think the easiest thing to do to find h is to go back up here. We have d, and so we will use that equation to find h. And we'll write our answer in a complete sentence. The helicopter is about 630 meters high, and it is about 810 meters from the nearest observer. Let's summarize what we did on our previous word problem. We first tried to make an accurate picture and make a right triangle as possible. Write a known trig ratio in the triangle that seems logical, but sometimes you have to use extra triangles like we did with the left and the right. We used two equations to figure out one of the two unknowns, and then we plugged it in and we solved for the variable that we did need. And remember to write your answer in a sentence. For the past few days, we have been very careful to be talking only about quadrant 1. And when I say that, I mean that we've only been talking about acute angles. Now we're going to use the same formulas, the same ideas, and we're going to expand it to any quadrant. So remember that we have our value that we have in generic form, and we have an angle theta that's in standard position. Its initial side is on the positive x-axis, and it shoots through a point xy, and we can get the value. We can drop a triangle and we can get a value for x and y and calculate r. Well, when we talked about the fact that this is only quadrant 1, if we move right for x and up for y, x and y are always positive. R has also been positive, but now we're going to do a little bit more with our conventions. And the same ideas are true for any angle, no matter what they are. So let's consider this right here, where we have taken an angle still in standard position because it starts on the positive x-axis, and we've rotated it anywhere. For this particular example, I just chose quadrant 2. But we notice that theta still starts from the positive x-axis, and it can end anywhere, including the second or the third or the fourth quadrants. Something very convenient that I'm sure you remember, but it's going to be positive. It's going to be helpful to remember these important things. When you go left for x, the x value is negative. When you go down for y, the y value is negative. Consider this next example. When you place an angle in standard position, we remember that its initial side will be on the positive x-axis, and the terminal side we will draw through approximately. We've gone 5 over, and like that, and we've gone about 2 up. So what we want to know is the values of all 6 trig functions. So we label that as theta, and we emphasize that it comes from the initial side. We drop a right angle down to the x-axis. We will never drop to the y-axis, always the x-axis. And let's put the labels on. Okay, so there's the coordinates, and that's y. Okay, how did that happen? Okay, we haven't figured out the value of r, so let's kind of go to the side. And it is the two legs of the triangle squared, which is 25 plus 4, square root of 29. Okay, so we'll put that on there. So we'll write sine theta, cosine theta, and tangent theta, and we will try to go right to the letters. Sine is y over r, cosine is x over r, and tangent is y over x. And I remember that sine of theta is y over r because y and the long I sound in sine kind of go together. That's how I remember it. So now let's fill in what we know. We know that all of the y's are 2. And we know that all of the r's are root 29. And then what we have to be very careful with is that the x is negative. So when we write the x, we make sure to remember that it's negative. And put them in proper form. But we've only done 3, so we need to do the reciprocal functions. And so what goes with sine? Cosecant, so I'll write that first. What goes with cosine? Secant. And what goes with tangent? That's the easy one, cotangent. And I just flipped over their ratios and flipped over these ratios to get their values, and they're all cleaned up. This is the same problem we had before, but we're going to look at it from a different lens. We are going to choose, well, let me write a little neater, any of the previous relationships that we wrote. They should all work, right? And let me change the color. Oops. So to save a little time, I just wrote sine and cosine in the relationships, and from the previous slide, sine of theta was 2 over root 29. We cleaned it up, but for this computation we can just keep it like that. And cosine of theta was negative 5 over root 29. And theoretically, we'll use either one of those and it shouldn't make any difference at all. So let's just do the top one first. And if we take the inverse sine of both sides, we get 21.8 degrees. And if you didn't really think about it, then maybe that would be okay. But here's what I'm going to write. Huh? Theta was definitely obtuse. Let's draw it again to show you and remind you that here was our axis. We went left 5 up 2. Our value of theta was definitely not 21.8 degrees. Okay, so let's keep going with cosine. So, inverse cosine of negative, remember not to forget the negative, 5 over root 29 degrees. Let's see if it gets us 21.8 as well. It's not looking that way. 158.2 degrees, which definitely seems reasonable if you looked at that approximation that we drew before. So the question is, why are these answers different? And to answer that question, we need to know about reference angles. And we need to remember the quadrants where x and y are positive and negative, like I brought up before. Well, we must account for the fact that there are two places where sine can be positive. Okay, that took forever. Let's consider the answer that made sense with our first one that the calculator gave us. So the calculator gave us 21.8 degrees. Okay, this looks pretty reasonable for 21.8 degrees. But we have gone up, so we have a positive y right here, and we have gone out. Let me highlight that instead. We have gone out a certain distance for our r, and r is always positive. So here in quadrant 1 we have a positive y and a positive r. We have a positive sine ratio. Well, consider this one over here. We have gone out a positive, out a positive r, and we have gone up a positive y. So we need to always be careful about the problem and be critical the way that we think about it. In this particular problem, when we use the calculator to give us sine, the inverse sine of 2 over square root of 29, it gave us the value of the reference angle. If you look at this, so we notice that there are two places for which we can have a positive sine ratio. What's the same between the two places? Well, the one in quadrant 1, this one right here, this one is the one that our calculator gave us. But this one to the right is an obtuse angle measure with the remaining right here, this part right here, the reference angle, is also 21.8 degrees. The correct answer is 158.2 because we know it's obtuse, but the calculator, when we did inverse sine, did not give us the right answer, and we'll talk about that in a couple slides. I'm doing the next couple slides a little bit out of order, and so we're going to bring back the big XY axis, and we'll talk a little bit about the reference angles. But before we do that, we need to think about each of the four quadrants and come up with this little way to remember which trig function is positive or negative in which quadrant. And so we come up with the letters A, S, T, C, which can stand for many things. You can think of it as all students take calculus, or you can think of it as a little bit more fun, all Saratoga teachers are cool, starting in quadrant 1 and rotating around in a counterclockwise manner. But what this means is, it means, I use just another color, I guess, of highlighter. All right. It means that all three main trig functions, and of course all six then, are positive in quadrant 1. Only sine, or its reciprocal cosecant, is positive in quadrant 2. Tangent and its reciprocal cotangent is positive in quadrant 3. And cosine and its reciprocal cosecant is positive, are the only two positive ones in quadrant 4. Now, of course, I don't want you to blindly memorize these. I want these to be tied in with your sine of theta is y over r, cosine of theta is x over r, etc., and think individually if it's negative or positive. Okay, but let me clear the ink from these, and what I'm going to show you now is the answer that your calculator is going to give you when you do inverse sine, inverse cosine, and inverse tangent. And we will come to the math in that a little bit later, but I'm going to emphasize that when you take an inverse trig function, your calculator has to give you the same answer every time, or you would worry that your calculator is not working right. And when we looked at before, we looked at sine versus cosine. Well, your calculator is going to give you the answer for cosine in quadrants 1 and 2. It's going to give you the answers for sine in quadrants 1 and 4, and it's going to give you the answers for tangent. Let's go aqua. Also in 1 and 4. And that is the only quadrants that your calculator will give you an answer for. Of course, we have to use our brain and know that there are two quadrants for each that could be positive or negative. And so let's look at the next slide to see how we might do that. Here's an example of using the signs of the different trig functions in the different quadrants and the reference angle. For this particular problem, it's going a little bit overboard to use the reference angle, but for trickier problems, you'll definitely need it. So the first step is always to draw a reasonable picture and see what you're going to get. We are looking for the tangent of 162. Note that I've included the reference angle in this particular shot. Yeah, that's right there, the reference angle. So all I did was subtract 162 from 180 degrees, and I got the reference angle. We know that that's the value of that acute angle. And then step 2, determine the sign, S-I-G-N, of your answer. So we could use the all students take calculus, or how I prefer to think about it is this value right here, y over x. And so we have a positive value, we've gone up for y, and we have gone left for x, and so positive over negative is always the same thing it has been, negative. So step 3, just using the reference angle, determine the magnitude. So let me pause just for a minute. And emphasize that here we are figuring out the sign of the answer using the all students take calculus, or using the positive over negative where the angle actually lay. And then here we're getting the magnitude, and we're treating that as two different independent values that we'll put together for the final answer. So tangent of 18 degrees, if you use your calculator, is 0.3249, chopped off to the 4th decimal place. And so step 4, we're going to put those together. We know that it's negative because it's in quadrant 2, and we're taking the tangent of it. And we know that the magnitude of the tangent is 0.3249.